First, let's finish the example. What we did last week, we found the transfer function of a system, closed loop system, based on system matrices in state space format. We figured out that GS, the output over input, is H. H is the output matrix, Si minus F inverse multiplied to G. G is the input vector plus J. Now, assume I have a system which is state space format. Is matrices are given as here. I have the system matrix F. I have the input vector J and output vector H and a scalar J. I want to see how can I find the Laplace transform or transfer function of this system using these system matrices. Before going further, before I forget, let me know. Next week we will have 3 hours control. Okay. I'm sure that you will enjoy it. You will have 3 hours control. Yes. And week 11 you don't have any control. Today I will finish the control, and next week I will try to solve different problems in state space format and the Laplace domain in order to see how to design controller, GID controller, or state space format controller. This week and next week you will have the tutorial. In tutorial I will give you time to work on your coursework project. So if you have any question in terms of MATLAB coding, it's a good time for you to ask your questions. And another thing, important point, is that there is no past papers for this module, for the control. And because it's the first time I'm teaching this control module. And there is no past exam. But the good point is that I won't ask you anything extra I give to you in tutorial and lecture time. Okay? If you know lecture times and lecture notes, all examples, definitions, everything, and your tutorial problems, for sure you will find. Okay? Okay, so let's start. To find the transfer function of this system, we need to use this relation. To find this relation, first I need to calculate the matrix Si minus F, take inverse of this matrix, and then calculate the transfer function. Okay, to do so, I have this relation. First, I calculate the matrix Si minus F. I is the matrix, identical matrix 2 by 2, multiplied to S. If you multiply S to matrix I minus F, you will get this 2 by 2 matrix. I need to find the inverse of this matrix. How can I find the inverse of the 2 by 2 matrix?
One of the determinant.
Okay. Yeah, you need to swap these elements and over the determinant. Okay. So if here is the determinant of the matrix, and here I just swap the diagonal components items and swap these elements on other diagonal. So when I calculate the Si minus F inverse, I have matrix H and J is 0, so G is 1, 0, H is 1, 2. Here is Si minus F inverse, and here is the determinant. So the transfer function will be S plus 2 over S squared plus 7S plus 12. So easy. Any question? No. Okay. So I will complete the state space format and control design using the state space format today, hopefully. And next week, we will review the whole lectures, whatever you learned so far, in order to how to design the control system in both state space format and domain and in Laplace domain. Okay, so what we have talked about so far. Last week we talked about the block diagram and the state space and analysis of the state equations. today I will talk about the dynamic response of the system using the state equations and design of the controller for the full state feedback. Again, the famous relation, GS is H SI minus F inverse J plus J. The important when you transform from the state space to Laplace domain, in Laplace domain, what property was the most important? Stability. And how we can check the stability of the system? Pole locations, exactly. If the all poles are in the left side of the complex plane, the system is stable. Otherwise, the system is unstable. So we want to see how we can determine the poles of the system using the system matrix we have, system matrices. First, let's again define some definitions. Last week, we saw that by transforming the state matrices to the diagonal form, the poles appears as the eigenvalues on main diagonal of the F matrix. How we figure it out? In which form we had the poles on the diagonal of the matrix F? Modal canonical form. Okay? So keep in your mind, if you use the modal canonical form, the poles of the system appears on the diagonal of matrix F. The definition of pole of a system, a pole of the transfer function GS is a value of S such that if S is equal to Pi, the system can respond to an initial condition as Ki e power Pit. Why? Anyone can show me why we have this response to initial condition? 40%. 40%. Why the response of the system, if I have a first order system, to initial condition will be Ki e power Pit? For the first order system. Any one to show me, to show the other students? 40%. No one?
I'm pretty sure that e to the minus st, sorry, e to the st is the inverse Laplace transform of 1 over s, but I'm not sure I've done it. Right. 80%.
You already have 40%.
Shall I get that? So anyone else? No?
Okay.
Right. I think this is law, so it can go.
Yeah.
Right, so if s equals pi, then, hang on, what is the function?
For the first order system.
So then you've got 1 over s plus tau, that's it, thank you. You can have 10% of that. Because that's the bit I was stuck on. So in frequency domain, so if f of s. Huh? Yes, you're right. Sorry, I can't understand. I know half of what I'm doing, I just don't know how to make it make sense. Technically, that other thing was a first order system. So if you got that, or in other words, 1 over tau pi plus 1. Well, you put that in there.
Okay.
P, sorry, that's not an I as in the
No, it's
expression.
not the correct. You won't get anywhere.
Okay, no. Okay. I was going to do an inverse Laplace transform of whatever that was, and hopefully end up with K.
I know you know somehow how.
Yeah, I know how to do it.
But it doesn't work for 40%. Give me.
Oh, right.
Okay. Do you know any idea?
God.
Okay. So let me explain to you. Look, we have a first order system. Y dot plus Pi y equal to 0. For the free response system, we don't have any form, external form. If I get the Laplace transform to solve this, the first order system, if I get the Laplace transform of this differential equation, what do I have? I have s, y of s minus y0. I assume y0 is equal to k, ki for example, plus pi ys is equal to 0. So if I factor out ys, I have s plus pi y of s is equal to y0, which y0 is ki, correct? So y of s is equal to ki over s plus pi, which means s is equal to minus pi. If I get the Laplace inverse of this one, ki is constant, so it will be ki 1 over s plus pi is equal to e minus pi t. Right? So this is the response of this system. Pi is the negative value. Here I have a negative value. If you assume pi is negative, this will be positive. Doesn't matter. It's just fine. Yeah.
So I think just now the Robin has explained that magic experience is that if s is equal to p then pi, which means that the power of the first order system is pi. Yeah.
Okay. Yeah. But I am sure it was taken time to get to this one. But okay. Anyway, so that's the reason for the having initial condition. If there is no external force for the free response, the response of the system will be ki e power minus pit or plus pit. That means you will define the pi positive or negative. So we know that the response of the first order system, if I don't have any external forces, will be ki e power pit. Pi is called pole of the system if you are in the Laplace domain. If you are in the space domain, it's called the natural frequency or natural mode. Do you know what's the natural frequency? What? What? 1 over omega n is the frequency at which we have the highest amplification from the dynamic module. We just taken the exam, midterm exam. Okay, so look, pi is exactly the same as the natural frequency of a system. There is no difference from the control module and dynamic module you are taking. But different approach, different language, but the concept is exactly the same. Okay, so now I want to see how can I find the poles of the system using SLS format. Any idea? 40%. Go on. Yeah. If I gave you this relation, how can you find the poles of the system? Poles of this?
By the eigenvalues of M.
Just a moment, your answer is not accepted because you have already taken mechanical quantity. Okay. What do you mean by expand the matrix?
Find the eigenvalues of M. Hey, it's true, man. That's true. Go on, don't keep it. It's true, man. Oh.
Just one dude.
Well, you have to know the eigenvalues of X.
Oh, he told you. Okay, let's see. To find that, how we can find the poles of the system, I assume, using this relation, I assume there is no external force to the system. If there is no external force to the system, it means u is 0. So I will have x dot equal to fx. And if I assume that the initial condition is given x at time 0 is equal to x naught, according to the relation I had here, the xt will be e power pit x naught. Here is the scalar differential. Here I have the vector differential. Here is the yt, but x is x1, x2, up to xn. Correct? But still, I have the first order differential equation. And the solution of the first order differential equation doesn't matter if you have the vector or you have just one variable, is the same. Is the exponential response. Here, ki is x naught, and pi is the poles of the system. So, if the solution is xt is given here, and I substitute to this relation, if I get the x dot t from this solution, I will have pi e power pit x naught. Is that true? Calculate x dot t from this relation. Will be pi e power pit x naught. Is that true or not? Okay. Pi is my pole of the system. If I calculate x dot, I have pi e power pit x naught, which is equal to fx. X dot is equal to fx, isn't it? And again, x is e power pit x naught. Isn't it? Look at the relation you have, the previous page. xt is e power pit x naught. If I get the derivative of that, I will have pi e power pit x naught, which is equal to fx. Again, if I substitute the value of xt here, the solution of xt, I have e power pit x naught. Look at this relation and this relation. So, f x naught is equal to pi x naught. Isn't it? This one and this one. E power pit will cancel out. You will have f x naught equal to pi x naught. Correct? Is that clear to everyone?
Yes.
Okay. So, I rewrite the equation. I bring the right hand side to the left hand side and factor out xi, x naught. But because I have the matrix here, I will have the identical matrix I. If I want to have the solution of this non-trivial solution of this relation, what condition should be satisfied? In which condition this relation has a non-trivial solution? Yes?
The determinant of the brackets.
Exactly. The determinant of this one should be 0. Okay? In order for any value of x naught, this will be 0. If I put determinant of the pi I minus f equal to 0, I have a solution for this one, non-trivial solution. What does it mean? What is this relation? Determinant of the pi minus f. What does it give to you? How do you calculate the eigenvalues of a matrix?
Exactly like that.
Exactly like this relation. You know how to calculate the determinant of the matrix, don't you? Okay.
Yes.
So this it means pi, which are the poles of the system, are exactly the same as eigenvalue of a matrix F. So, if you have the system in the state space domain or format, in order to see if the system is stable or not, you need to find the eigenvalues of the matrix F. If all eigenvalues are negative, the system is stable. It means that you have the all poles in the left hand side. Clear? Clear? No? Which part is not clear? Tell me, I will explain again. Pardon? Is it okay? Okay. Don't ask me, explain again from beginning. Okay. Look, what was xt? Look at your lecture note.
No, no, the second to the third line.
This one?
No.
Here?
Yeah.
Just look at these two relations. This one is equal to this one.
No, no. From
Yeah?
yeah. How do you get
Okay. Look at this one and this one. This is equal to this one.
Yeah.
E power pi t will cancel out with this one. So pi x naught is equal to f x naught.
Yeah, then how do you get to the one below?
Here I factor out, I bring the my pi x naught, or sorry, f x naught to right hand side. I factor out x naught. Here is the matrix f. Pi is the variable, is the scalar. If you want to factor out x naught, you need to multiply to the identical matrix. Okay? Yes.
What did you say about the solution to what is your equation?
Look, if
The value to that.
if the terminal is not zero, okay, the only solution will be x not equal to zero, which is not the solution I want. I want to find solution for any kind of the initial condition. The only answer will be when this determinant is zero. Okay.
What did you say about negative values?
Okay. So pi, the eigenvalues of this f are the poles of the system. We know the system is stable if the all poles are in the left hand side. So if eigenvalues of f is exactly the poles of the system, it means all should be negative in order to have the poles in the left hand side. Correct? So we figured out how to find the poles of the system in state space form or representation. What will be the next question? What will be the next question? Zero. What will be the zero of the system if this system, the matrix is given? To calculate the zeros of the system, we need to follow the same approach, but a little complicated. But before that, the poles of the transfer function are the eigenvalues of the system matrix F. Is a very important statement. If by any chance you want to continue your education in control systems or your future career in the control, as a control engineer, is very important, this statement. The system is, the poles of the transfer function is exactly the eigenvalues of the matrix F. So, similar to the Laplace domain, the determinant equation, determinant of the pi minus f equal to 0 is a polynomial in the eigenvalue pi known as characteristic equations. Look, I told you I will give you 40%. Why? If you look at the relation in the first slide, GS is HSI minus F inverse J. What's the denominator of this one is determinant of the matrix SI minus F.
Determine pi minus f.
So just a moment, look. GS is equal to H SI minus F inverse J plus J. Usually J is 0. Okay? So it will be equal to H something matrix over determinant of SI minus F J. So look, this one is your characteristic equation in the Laplace domain. We prove it. We prove that the eigenvalues of F is exactly the poles of the system. Again, if you look at the example I showed you in the previous, the example from the last lecture, if you look at the denominator, it was the s squared plus 7s plus 12. I think so. Isn't it? Wasn't. If you calculate the determinant of the matrix F, will be exactly s squared plus 7s plus 12. Okay. Now I want to find zeros of the system. 40%. What was the definition of the zero?
Oh, wait.
I know the zero.
Definition the
But
zero.
what's the physical meaning? Why we call it zero?
Oh, it's when the system is able to become stable.
Roots of the non.
Nope. What? Why?
Hey, that's
When?
what I said.
Why at zero is the response is zero? Don't look at the Pardon? Okay, I know you look at the lecture. Why, in which condition you have the input and output? I explained to first lecture. If find zero, we call it the root of the denominator. Zero because you have
I was gonna say that, but you.
no, you say the roots. The
Yeah,
roots
roots
is
of the
total-
num-
No, no, it's not the I was a student someday. Don't.
I was literally.
Yeah. The way you are going now, I went 10 years ago. Okay.
Time goes by.
We call it zero if the frequency of the input is exactly the same as the frequency of the zero, the output response will be zero. If the input frequency is exactly the same as the frequency of the zero, which means the zero of the system, the response will be zero. That's why we call it the root of the denominator zero. So, again, all of you look at it. A zero is the value of S such that the system can have a non-zero input and a state and yet have an output of zero because the frequency of the input is the same as frequency of the denominator or zero of the system. Frequency of the input is equal to frequency of the denominator. So, to find the zeros of the system, I assume I have the input u naught equal to e power z it. Okay? Such an input. If, according to the definition of the zero, if the frequency of the, look, I have zi here. Zi is 0. If this polynomial is the same as the zero of the system, yt will be identically equal to 0. No response. In this case, u will be equal to u e power z it, xt will be equal to x naught e power z it, and yt will be equal to 0. 40%. Why this one is equal to x naught e power z it?
Oh, can you ask that question again, please? Can you ask again one more thing?
Why xt is equal to x naught e power e z it if the input is in the form of e power u e power z it?
Is it the steady state solution?
No.
Because x naught is equal to u.
Time out. Not correct. First problem in the first tutorial. If you look at the first problem of the first tutorial, it was to prove using, what was the name of that? Using the impulse function. Okay? To find the response of the system. If I have such input, the response of the first order system will be, the output will be in this format. Look at your first problem of the first lecture, this first tutorial. Okay, assuming this is correct, if, look, again, x t is x naught e power z I t. If I get the derivative of this function, I will have z I x naught e power z I t, similar to the whole system. So I have the x naught equal to z I e power z I t x naught will be equal to fx, which x is e power z I t x naught plus g u naught e power z I t. This one is u. I assume u is equal to u naught e power z I t. So if I factor out x naught and u naught and rewrite in the matrix format, look here, I have what? Zi e power zi t x naught equal to f e power zi t x naught, tell us g u naught e power zi t. E power zi t will be cancelled out from all parts. So I will have zi multiplied to I x naught minus f x naught minus g u naught equal to 0. If I want to reshape this one in the matrix format, I can write like this: zi I minus f minus g x naught u naught equal to 0. If you do this multiplication, the first element will be zi I minus f multiplied to x naught, this part, minus g multiplied to u naught, this part, equal to 0. Okay? I just reshape this relation in the matrix format. But the output is equal to hx plus ju. Again, I substitute x, xt is equal to e power zi t x naught, and u is equal to u naught e power zi t. If I combine, again, write this formulation in terms of the x naught and u naught, and combine this one with this relation, I will come with this format, matrix format. Correct? Is that clear to everyone? So, in order to have a non-trivial solution for this one, what condition should be satisfied? The determinant of this matrix be equal to 0. So, if I put determinant of this matrix equal to 0 and find zi, I will count the zeros of the transfer function from the system matrix. Is that clear to everyone? Question? Any questions? No? Mark? I can just everyone. After clear? Yes. Okay. I know clear to you. Okay. So look, I can find the Laplace transform from system matrices in two ways. One, from the determinant of the zeros, because look, determinant of the zeros, this one give me the zeros of the system, and determinant of this one give me the characteristic equation of the system. So this one over this one give me the transfer function, or I can use this gs over equal to hsi minus f inverse plus g plus. The only problem with this relation is that numerically, if you want to use the numerical method to solve the problem, this one maybe you will face some numerical problem if it is not, the poles location are not good, are so close to each other or very close to the imaginary axis, you won't have a nice numerical solution for that one. But in theoretical point of view, both are the same. Okay, analytically, both are the same, exactly the same. You can use each formulation to find the transfer function of the system using the state space representation or state space matrices. Clear to everyone? Okay. So let's have a look at an example to see how we can find the poles and zeros of the system. I have this system, a thermal system, is SL space is represented by these matrices. I want to see First, if the system is stable. The second, if I have any zero. To find the system, either the system is stable or not, what should I do? Poles. I need to find the poles. How can I find the poles of the system? Determinant. I need to find the eigenvalues of the matrix F. To find the eigenvalues of the matrix F, I calculate the determinant of the Si minus F. If you do this calculation, again, I is the identical matrix, F is the system matrix. If I do calculation and find the determinant of this matrix, I will come up with the roots or eigenvalues -4 and -3. So the system is stable because I have two poles, real poles in the left-hand side of the complex plane. Right? Any question?
Yeah, just back in the derivation, might we be asked in the exam to derive how to find the poles?
Everything is possible. Everything is possible. As I said, whatever I say in the lecture syllabus and tutorial is possible. Outside of it is not possible. Okay? The assessment purpose is that I make sure everybody understood the concept of the concept. Okay, guys. So we want to find zeros of the system. If I want to find the zeros of the system, if I form the matrix, I will come up. I need to find the determinant of this matrix. How can I calculate the determinant of the 3 by 3 matrix? Cross the first row and first column. S multiplied to 0, 0 multiplied to 0 will be 0. The first row and the second row, -1 by 0, 0 by 1, 0. The first row, third column, I will have -1 multiplied to -1 by 2, -3, minus S. So -2, minus S multiplied to -1 will be S plus 2 equal to 0. So I have 1, 0 at -2. So the transfer function will be S plus 2 over S plus 3 multiplied to S plus 4 or equal to S plus 2, S squared plus 7S plus 12. If you look at the previous example, you get the same transfer function. Okay, the example I solved in the beginning of the session today. So both the same relation, but different methodology. Okay, any question? If you want to make sure about your solution, you can use the MATLAB command steady state. Using the command steady state SS, F, G, H, and J, you will get the system G. And from T0, system G, you will find the zero and poles of the system. So this one. Okay, I think you worth to have a 10 minutes break. And next hour I will finish the control law design using the SPSS format, and I think it's better to close the chapter of the control today. And next week, save the video.